Nice to see you, everybody. We start. And I will repeat the definition of the symplectic leaf of a Poisson variety, which was given last time. So we work in the framework of some Poisson variety. we can think about it like as an affine space Rm with a bivector Pij d dxi d of dxj with the summation with x just variables on this affine space, but we can think about it in a little bit more general context if M is a Poisson variety. And we discussed the relation of the Poisson structure with the symplectic one. I'd like just to remind you this definition. So if pi is non-degenerate, then omega, which is pi minus 1, corresponds to some differential form pi ij dxi dxj. This differential geometrical object encodes the same information principally, but only in the situation of the non-degenerate Poisson structure. What can we else I'd like to recall you that for each function it's infinity m we associate a Hamiltonian vector field which is minus pi applied to the differential of h and is written as minus d pi ij over dx. I'm sorry, no, like this, minus pi ij dh over dxj d over dxi. So it's a vector field. And what else? There is a very useful formula that in the situation of the non-degenerate Poisson structure, the Poisson bracket between functions can be calculated as an application of this differential form to the corresponding Hamiltonian vector fields. So maybe it will be task 1 for the homework to verify this formula. But it is principal for us that the symplectic form in the situation of the non-degenerate Poisson structure encodes principally the same information. So we can calculate the Poisson bracket by the help of the symplectic form. Okay. And this, the next idea is the following one. So when the Poisson bivector is degenerate, it is principally the same thing as to have Casimir functions. Comment. If C is a Casimir function, So it is an element of the center of this Poisson algebra. Then DC lies in the kernel of the bivector of pi. It means so it's a point P of our variety M. Bivector, we can correspond it as a bilinear function on the cotangent bundle. So DC is the dual space to the tangent bundle to M, and DC is a vector in this cotangent space. And the fact that C is a Casimir function means that pi applied to DC to df is equal 0 for all f. It means that this bilinear function has a kernel. And from the linear algebra, you should know that in this case, the rank of this bilinear function is less than the complete form, less than the dimension of the space M. The co-rank of pi is non-trivial, so it is degenerate. So in a sense, the existence of Casimir functions on our Poisson variety is equivalent to the degeneracy of the Poisson structure. And more generally, I'd like to notice it as a fact without demonstration, but the fact is the following, that the co-rank of pi in a generic point in a generic point is equal to the dimension, to the functional dimension of the center. Functional dimension. So it means the number of independent variables in this ring, in the ring of central functions. Please ask if some notions look like declarations. I could provide some comments and some references to other courses in your program. Okay, but morally, for the moment, the principal thing is that the the central functions they describe how degenerate the Poisson bivector is. And definition, which was a week ago, it was also like declaration, but it relies on all these considerations. A generic symplectic leaf is a level set M C of all x, that's C of x, Ci of x is a constant Ci for all Ci from the center. So it means that we fixed all the values of all central elements. And then this subvariety is called the generic symplectic leaf. In the statement, also as a fact, we will see it in examples, but it is a general statement that for generic C, it means the choice of central values MC is a symplectic manifold. Comment to this fact. To fact. To. How to illustrate this fact? So we have our manifold, and our manifold, it's better to be a three-dimensional at least. So for example, our manifold is R3, and this manifold is foliated as a variety of two-dimensional leaves. And in this direction, we have a function C. So it's a gradient of the function C. And this function C is, so this is the gradient of C. And this C is a central function. And if we fix the value of the function C, we obtain a level set MC. So it's a big function C. This level set is big function C equals small function, small c, which is a number. And if we consider some neighborhood of this point, then the Poisson bivector in direction of in fact, not gradient, but just the differential of C. In the direction of the differential of C is trivial. It is equivalent to the fact that C is a central function. But there are two other directions in this three-dimensional space, which is the cotangent space to our variety, our manifold, for which the Poisson bivector is not degenerate. And it means that on this level set, we can define the symplectic structure. So this is an idea. Is it principally clear? Okay. In this framework of Liouville integrability, we will be interested in symplectic manifolds. That's why it will be always important to us to find Casimir functions and to describe in some coordinate the symplectic leaves who are just a level set of Casimir functions. So this will be important in our constructions. But Now we will start to consider some concrete examples of of Hamiltonian systems. Examples of Hamiltonian systems. And the first very important example is the Kepler problem. And we will work in Hamiltonian formalism at the beginning. So we describe. So the Kepler problem, you know, it is the problem of movement of a body in the gravitational field of the heart of the big body, like like the sun. So it's the sun. It is our Earth, and the energy is described by the kinetic term p square and by some potential form term which will be like this. So here q is the coordinate of our point q1, q2, q3. It's Earth with coordinates q1, q2, q3. And pi p is the momentum. Here is the absolute value of this vector, and the Poisson bracket is canonical. So the bivector pi is the sum of d over dq I. I'm sorry, dpi dqi I from 1 to 3. Sun 0, 0, 0. So what are the Hamiltonian equations in this system? So we will work just by definition. So qi dot is h qi, the Poisson bracket, and okay, I will write it for the first time just directly. It's alpha q qi, but I will use the Leibniz rule and the Poisson bracket of generators here. So this Poisson vector means that pi pj is equal 0, qi qj is also trivial, and pi qj is delta ij. And then I will use the Leibniz rule to calculate all the Poisson bracket. So it is linear. So the Poisson bracket of this term is trivial because q with q is always 0 with all components. So the only non-trivial part is here, and it is equal 1 over 2 p1 plus p2 p3 qi and it is just pi. There is no. I'm sorry. There is no square. It is just this. Just the square of the distance. Like this. Is it okay? Yes? So we can think about the Leibniz rule. So the only non-trivial Poisson bracket here with the same I. So we can replace it by over 2 pi square with qi. And here we calculate it by the Leibniz rule. So it's 1, 2 pi, and I'm sorry, yeah, like this. And here, I'm really sorry. Pi, qi, and this is pi. Okay. The next Poisson bracket, it's a little bit more complicated, but I will try h pi, and it is 1 p square alpha q pi. So in this case, this Poisson bracket is trivial. The only non-trivial one is here, minus alpha. I will write it as the sum of qi square power minus 1 over 2 pi. We should differentiate it by the Leibniz rule. So it is minus alpha minus 1 over 2 this term power minus 3 over 2. Okay, and now we should calculate the Poisson bracket of the corresponding qi j. So we should choose here j equal I, and then it will be 2 qi. Okay. With one mistake. So I have chosen the wrong sign, because here I calculated. So it's better to write qi pi. Okay, like this it will be correct. So like this, and it will be minus alpha qi, absolute value of q power 3. So I will summarize that qi dot is equal pi, and pi dot is equal minus alpha qi q the absolute value of q power 3. And it means that we can write the second derivative of the vector of coordinates just minus alpha the vector q 3. So it is a known equation of motion in gravitational field of the big body. So we extracted very important knowledge that known and useful equation can be put into the Hamiltonian form. Now it is important to us to discuss Casimir functions and integrals of this motion. So the first question is to describe the center, Casimir functions. What do you think about Casimir functions in this model? In fact, you know, but maybe in this new context. Who know the Casimir functions in this situation? So in fact, everybody know, but who can say, who can describe the Casimir functions in this case? So it is the question of the bivector.
Well, from physics point of view, I think it must be something like angular momentum or something.
You are right, but the angular momentum are integrals, and Casimir functions are integrals of every motion. So they describe the center of the Poisson structure, and we have discussed it already. So that this Poisson structure is non-degenerate. It means that its center contains only the constant functions. It's an important question. You have to know the answer. So here the center is just R. So it's the subring of constant functions. But integrals, it's a non-trivial and very interesting question. And you are right. The angular momentum provides integrals of this motion, and the angular momentum is the vector P Q. It is the vector product of two vectors, of the vector of coordinates and the vector of momenta. Let us write it in coordinates. So PQ is a vector with coordinates. P2, Q2, P3, Q3, P1, Q1. Let us calculate its dynamical equations. So normally it is denoted as J. So I'd like to calculate its dynamics. And it is described by the Poisson bracket of our functions with this vector valued functions, vector valued function. But we know that the vector product of two vectors is a bilinear operation. So I can calculate it as PQ. And it is H P Q plus P HQ. So this expression is bilinear in terms of P and Q. It is vector valued, but it is not very important. So it is a bilinear. So we can calculate the Poisson bracket of J with respect to the Hamiltonian vector field XH, just evaluating this Leibniz rule, evaluating this vector product by the Leibniz rule. So this is the way how to calculate it rapidly. And then we will use these formulas in a vector form. So what does it mean? H with the vector Q is just the vector P. And from this, H with the vector P is just minus alpha multiplied by a constant, I mean by the scalar function, but here we will have the vector Q. It means that what we have here, HP is proportional to the vector Q minus alpha over Q and with the vector product with Q. And the next term, this one, is plus P and H Poisson bracket with the vector Q. It is the vector P. I suppose you see that it is trivial. It is 0. Because we always have the vector product of the same vectors. And they are both 0 because the vector product is skew-symmetric. Okay? Okay, and it is a very important tool to solve this system. So it will be the question of the next big subject.
Sorry, why could we do the bracket of HPQ in that way? I mean, the second equation.
I'm sorry?
Now the next. Yes. Why could we do in
this one?
Yes.
You see, the vector product is a bilinear function on its arguments. It could be seen in coordinates. So it depends linearly on the coordinates of the arguments of P and Q. And when they calculate the Poisson brackets of H with the coordinates of this vector, it's the same thing as to apply it to the, by the Leibniz rule to this bilinear operation. So we can calculate firstly the Poisson bracket with coordinates of the vector P, and then calculate the and then to calculate the plus, and then to calculate the Poisson bracket with the coordinates of the vector q. So, but it's even simpler to consider it in vector terms. So we can apply Poisson bracket to the function h and a vector. It will be again a vector, as here. You see, here in these formulas, q is a vector. And we can calculate the Poisson bracket of h, a function, with all coordinates of vector q. And we will obtain the vector p. So this is very, very convenient notations for vector calculations. Is it a little bit clearer?
Okay, thank you.
Okay. Okay. So what's the result? That we have a dynamics defined by this Hamiltonian. You see, you know that the Hamiltonian is always an integral. Okay. And there are three integrals which are components of the angular momentum vector. We have demonstrated that this vector itself is an integral, so all its coordinates are integrals. So it, for example, it follows from this consideration that Lemma, the trajectories lie in planes. It follows from the fact that the along the dynamics, angular momentum is constant. Proof. J dot is 0. So J is a constant, J0. So it doesn't depend on time along the trajectories of our system. And it is some vector. And we know that J with Q, just a scalar product, you know, the scalar product is, by our definition, is P Q Q, which is 0. Okay. So because it's a volume of a parallelepiped generated by 3 vectors and 2 vectors inside, so it's 0, and it is a constant. It is a scalar product. It means that so here is J0, and we see that and here is the vector Q, and here is a projection of Q to the direction of J0. And it is constant. I'm sorry, it is 0. It is 0. The projection of Q to the direction of J0. It means that Q lies in the plane perpendicular to J0. It means that Q along the trajectories of our system lies always in some plane, in plane perpendicular to J0. So it is a very important property, and the existence of such integrals reduces the dimension of the space when we start to study the behavior of this dynamical system. So we continue our way to the Liouville integrability theorem, but we start by considering such an examples in the second task. Second task for the homework will be the following. Task 1, task 2. In Kepler problem, to find family of three independent integrals in involution. It means I1, I2, and I3 such that H, I is 0. It means that the integrals and Ij are also 0. So this will be the very important properties providing the complete integrability. So providing the existence of some expression, some procedure to obtain solution in quadratures. Comment to this comment. So we have found a vector of angular momentum, which is a vector with 3 coordinates, and all of them are integrals. So the Poisson commute Ji H Ji is equal 0. So they're integrals, but they do not Poisson commute between themselves. J1, J2 is not equal 0. So how to calculate it? Let us calculate it in coordinates. So J1 is just the determinant pi 2 pi 3 Q2 Q3, or P2 Q3 minus P3 Q2, and J2 is P minus P1 P1 P3 Q1 Q3, and it is equal minus P1 Q3 plus P3 Q1. Then if we calculate J1, J2, P1 Q3 minus P3 Q2, P3 Q1 minus P1 Q3. So it's bilinear, so we should calculate all all terms with all terms. If we calculate these two terms, we obtain -1 as the Poisson bracket of Q3 and P3. And we get -1 Q1 P2. Q1 P2. When we calculate this Poisson bracket, it's trivial because the indices of P and Q are different. In this case, it is also 0. And this one gives P1 Q2 plus P1 Q2. And this is exactly J3. J3, which is the determinant P2, Q1, Q2. So in fact, these generators, they correspond to SO3. So they have the Poisson bracket corresponding to this Lie algebra. You remember that? So it's the space of antisymmetric matrices 3 by 3. It is a three-dimensional space, and the commutator on matrices restricts well to the space of skew-symmetric matrices. And so these generators are good generators in this algebra. And it was a demonstration that these integrals, the coefficients of the angular momentum vector, who are integrals, they are not in involution. And here, in fact, there are 4 integrals. There is a Hamiltonian and 3 components of the angular momentum vector. In general, the number of integrals in involution in the symplectic case is restricted by the half of the dimension of this symplectic space. So your task is to find such a set of integrals. So the crucial condition is the involutivity condition of these integrals. Independent. Do you understand what is the independence condition here? So in simple words, it means that you can't express one of these integrals in terms of others, but more rigorous way to define it independence. The differentials, d1 are linearly independent. Or in other terms, the Jacobi matrix, which is the matrix of I over dxj, has rank the full rank. So this example is clear, and you have a task for the homework.
Sorry, a small problem that PQ here are coordinate function, right? So
yeah.
When we say PQ and J are vector, what is the vector space? I mean,
just three-dimensional space. Just R3.
but they are coordinate function now. They are
Yeah.
not.
But okay, P1, P3, Q1, Q1, Q2, Q3 are coordinate functions, and we can consider this is a coordinate vector function on the phase space. What's the difficulty?
Okay.
So it's a vector function on the phase space. You are right, but you can calculate its Poisson brackets by coordinates. I'd like to write again the formula, which is very useful. The formula of Hamiltonian equations. You remember that Q dot is P as vectors. So, but it means that Qi dot is Pi. But it means that you can write this equation just in vector form. And P dot is minus alpha Q over the length of the vector Q in the third power. But it also means that this it is the same as to write down Pi dot is equal minus alpha Qi over, again, the length of the full vector Q power 3. So it is just the equivalent form, but it is very useful in vector calculations because it's very very simple to calculate now P Q dot just by the Leibniz rule, because the vector product is bilinear. It is P dot Q plus P Q dot. Do you agree? And using these formulas, this formula and this formula, we see immediately that it is zero. Please keep it in mind. We will use some generalization of these formulas. So along this course, we will interpret familiar objects as some structures from linear algebra. So we will use some more general manners to calculate the very known things. Okay. So this is the second task related to the Kepler problem, and now we will discuss another very famous class of systems. So you maybe know better than me different tops, different even integrable tops in physics. So it is described by the vector which is the angular momentum and by the vector of angular velocity. And the equation is written in this form. There again, it is the vector product. And traditionally, one goes to the good coordinate system when in which J is related with the angular velocity by matrix I, which is diagonal matrix. Diagonal matrix 1, I2, I3. This matrix is called the inertia operator, and it is form the equation takes the following particular expression. I'm sorry. 3. Dot. We have here the same Poisson bracket as for the angular momentum in the Kepler problem. J2, J3 is equal to J1, and J3, J1 is equal to J2. So first of all, let us demonstrate that the length of this angular momentum is a Casimir function, which is the sum of Ji squared. Is a Casimir function. I will calculate it directly. So I will calculate the Poisson bracket of this vector C with J1. J1, so it is J1 square plus J2 square plus J3 square with J1. This is trivial, so there are two terms here. There are two terms, and there are two J2, J1, and plus 2 J3, J1. Then J2, J1, it is minus J3, minus 2 J2, J3, J3, and J3, J1 is J2, J3, J1. So it is equal 0 because the signs are different. Okay. Is it clear that all other calculations are similar? Okay, I will do it. J1, J2, plus 2 J3, J2. J1, J2 is J3 is equal to J1, J3 plus 2 J3, J2 is minus J1, 0. So maybe it could be obtained from some other arguments. So this J1, J2, J3 are generators of the algebra SO3, and this Casimir function is something like the length, which is preserved by orthogonal rotations. So that's why it is an integral, a Casimir function, but it could be verified directly. Okay, and in this case, you see, we have a three-dimensional space and one integral, C. MC is a point J1, J2, J3 such that J1 square plus J2 square plus J3 square is equal C. So it's a two-sphere. It's a two-sphere in a three-dimensional space. It is S2 in R3, two-dimensional sphere. How to understand that it is a symplectic manifold? So we'd like to restrict our Poisson structure on a three-dimensional space to the level set of the Casimir function. We get a Poisson structure on a sphere because so it can be restricted to the functions of the level set of the Casimir function. It is so the Poisson structure. It could be degenerate, and if so, it is trivial because the dimension of this space is 2. Do you understand this? Okay, so if it is degenerate, then it is trivial. But we know that there are non-trivial Poisson brackets between functions. So it means that this level set is non-trivial symplectic variety. It has a non-trivial Poisson structure symplectic variety. It is a symplectic variety. It is a very famous symplectic structure on the sphere, but so for the moment it is important for us that it is symplectic. So there are some conjugated coordinates P and Q on this variety. And we can write all we need just as if we are in canonical coordinates, in P and Q coordinates. Okay. The only thing to do is to interpret this dynamics as the Hamiltonian dynamics. And this statement is the following. Lemma. the Euler top dynamics, Euler top is Hamiltonian with h is equal 1/2 square I1 I2 3 square I3. So you remember this constant are some inertia characteristic of our rigid body. So we suppose that there is some constant, not coincident constant. So it's a generic body with some generic set of the inertia coefficients. Okay, how to demonstrate it? Maybe it will be task free to demonstrate this lemma. And now we start our great subject, it's a Liouville integrability theorem. But I'd like to say also that there are different approaches to integrability, but all of them are related with some explicit procedure to constructing solutions. In several situations, for example, in the case of the Todo system, of the full symmetric Todo system, we will discuss all different approaches to integrability. And maybe the general properties of all this construction of all these concepts, it's the difference with the chaotic dynamics. So if you can find all solutions in quadratures or in some other analytic forms by some algebraic procedures, it means that it is not chaotic. But the Liouville-Arnold integrability is the very concrete concept, quite general, but it appears different approaches. Just recently, just last week, I was at a conference in Yaroslavl, a conference on integrable system and dynamics, and my report was about the Lie-Bianchi integrability. So it's another approach. It is also efficient and is also related. It is also related with some algebraic structures, some symmetries of the dynamics. So there are different ways to treat and to use the integrability. Okay, but we'll start by this one, which is very general and very interesting from the mathematical point of view. So we consider a Poisson variety. Please think about it as you like. So as a general Poisson variety, or just in a affine space Rn with a bivector. The dimension. I'm sorry. We will speak about symplectic varieties now. Symplectic variety. Variety of dimension 2n. And we say a Hamiltonian system. You see, the Hamiltonian system is related with a function. Is called completely integrable. If there is a family, H1, Hn of independent integrals in involution. It means that H with Hi is 0, family of independent integrals. So these functions are integrals of this Hamiltonian dynamics. It means that such Poisson brackets are trivial. The first point. Second point, that in involution, Hi, Hj is equal 0 for all I and j. And the independence means, like in the case of the Kepler problem, the condition on the rank of the Jacobi matrix. So dHi over dxj, it's a matrix of all partial derivatives of our functions with respect to the local coordinates on our symplectic variety. But you see here the I goes from 1 to n and j goes from 1 to 2n. But we need that the rank of this matrix is n. So this means the independence of these functions. So a symplectic variety, on this symplectic variety, a Hamiltonian system defined by a function h is called completely integrable if there is a family of independent integrals in involution for such a system. Okay, so this set of conditions will be important for us for the following reason. So it's of Liouville and Arnold. So some interpretation are more recent. I don't know. So if M maybe H is a completely integrable system, then MH, we define such subvarieties which are level set of all H. So it's better to say here H and the set Hi is, because it's a condition on H and some family of functions. So all this data are in the definition of an integrable system. so we consider the level set of the integrals. The points of M such that hi of M is equal to some constant hi. So the first point is that the level set of integrals are invariant with respect to the Hamiltonian vector fields x hi. So it's quite simple, but you see it is very important in this program to reduce the phase space of our dynamics. So if we know that there are integrals which are in involution, so all this level set will be invariant with respect to all Hamiltonian fields in our family. So not only of our Hamiltonian vector field, and it is important. So we can introduce variables like hi and ti. Also in the foliated space. So these are some mh, and the coordinate h goes transversally hi transversally to this foliation, and times are just the times along the trajectories of Hamiltonian vector fields. So these are coordinates ti, tj, and here are coordinates along the values of integrals of motion. So we can introduce in neighborhood of each point one could introduce coordinates hi, ti, such that ti are times along Hamiltonian vector fields. You see, this is also quite a trivial observation if you understand that these are the times along vector fields of our integrals. See, the involutivity condition here means that we can introduce such coordinates. If not, it is not flat. So you can define the coordinates. You see, there are trajectories of two types, and the fact they commute, the corresponding vector field commute, means that if you define a translation of t1 and then a translation along the other time t2, and then do it in the opposite order, you obtain the same point. It means that the corresponding vector fields commute. But if not, you couldn't introduce such a coordinate. So this simple property is an effect of the involutivity of our functions, of integrals, and consequently by the corresponding Hamiltonian vector fields. So it's a non-trivial consequence of the involutivity of our integrals. Next, one could say many things about these level sets. So if M H is connected and compact, then MH is just the n-dimensional torus. And compact. So it's bounded if you want. It's lie in some maybe big ball. So if it is connected and compact, then it is just the n-dimensional torus. If it is not compact, but connected, then H to K R n minus K. So there could be some non-compact directions. So it's a direct product of some torus of lower dimension, and the rest is given by non-compact direction. It means that the motion is not periodic. It has some attraction points, or so it's not compact. And the last one, last and very important point. So if MH is connected in compact and compact in a neighborhood of a point, in a neighborhood of a point M, it means that so this is the point M, the level set which passes through this point M is some torus, but in the neighborhood of M, all the level set are also tori. Then in the neighborhood of M, one could introduce coordinates I and phi such that the symplectic form is canonical in these coordinates di I, d phi I. The I are just functions on Hamiltonians, so the integrals. Constants for all for all Hamiltonian fields corresponding to II, and phi I are canonical coordinates on Tn. It means canonical angle variables. It means that the periods are the periods of phi I are 2 pi. Just the angles along the periodic cycles on the tori. And moreover, these functions I and phi I are given by quadratures from initial coordinates, from initial on M. Okay, I suppose we will discuss some steps in demonstration of this theorem next Monday. We finish our lecture for today. After 15-minute break, we will have a seminar part.